delta x, delta y, delta z to get an approximation formula. Which is delta f is approximately equal to f sub x delta x plus fy delta y plus fz delta z. So it's getting cramped, but I'm sure you know what's going here. So, and observe how this one is actually equal while that one is approximately equal. So they're really not the same. Another thing that the notation suggests we can do, and I claim we can do, is divide everything by some variable that everybody depends on. So say, for example, that x, y, and z actually depend on some parameter t. Then they will vary at a certain rate, dx dt, dy dt, dz dt. And what the differential will tell us, then, is the rate of change of f as a function of t when you plug in these values of x, y, z. You will get df dt by dividing everything by dt in here. Okay, so the third thing we can do is divide by, say, something like dt to get an infinitesimal rate of change. For instance, well, let me just say a rate of change. Okay, so df dt equals f sub x dx dt plus f sub y dy dt plus f sub z dz dt, and that corresponds to the situation where x is a function of t, y is a function of t, and z is a function of t. Then that means you can plug in these values into f to get, well, the value of f will depend on t, and then you can find the rate of change with t of the value of f. Okay? So these are the basic rules. And this is known as the chain rule. It's one instance of the chain rule, which tells you when you have a function that depends on something and that something in turn depends on something else, how to find the rate of change of a function on the new variable in terms of the derivatives of the function and also the dependence between the various variables. Okay, any questions so far? No? Okay, so a word of warning in particular about, what I said up here. It's kind of unfortunate, but the textbook actually has a serious mistake on that. I mean, they do have a couple of formulas where they mix a d with a delta, and I would like you not to do that, please. Okay? So, I mean, there's d's and there's deltas, and basically they don't live in the same world. They don't see each other. The textbook is lying to you. Okay. So let's see. I mean, here I made, so the first and the second claims I don't really need to justify because the first one is just, stating some general principle, but I'm not making a precise mathematical claim. The second one, well, I mean, we know that approximation formula already, so I don't need to justify it for you. But on the other hand, this formula here, I mean, you probably have a right to expect some, reason for why this works. Why is this valid? After all, I first told you we have these new mysterious objects, and then I'm telling you, well, we can do that. But, I kind of pulled it out of my hat. I mean, I don't have a hat, but... So Okay, so why is this valid? How can I get to this? So here's a first attempt at justifying how to get there. Okay, so let's see. Well, we said df is f sub x dx plus f sub y dy plus f sub z dz. But we know, well, if x is a function of t, then dx is x prime of t dt, or dx dt dt, as you prefer. Okay? dy is y prime of t dt, dz is z prime of t dt. So if we plug these into that formula, we'll get that df is f sub x times x prime of t dt plus f sub y, y prime of t dt plus f sub z, z prime of t dt. And now, well, if I have a relation between df and dt, see, I got df equals something times dt. That means the rate of change of f with respect to t should be that coefficient. So if I divide by dt, then I get the formula that's, well, I get the chain rule. Now, well, that kind of works, but that shouldn't be completely satisfactory. Let's say that you're a true skeptic and you don't believe in differentials yet. Then, it's maybe not very good that I actually used more of these differential notations in deriving the answer. So that's actually not how it's proved. The way in which you prove the chain rule is not this way. Because we shouldn't have too much trust in differentials just yet. I mean, at the end of today's lecture, yes, probably we should believe in them. But so far, we should still be a little bit, reluctant to believe, this kind of strange objects telling us weird things. So here's a better way to think about it. So one thing that we have trust in so far are approximation formulas. At least we should have trust in them. So we should believe that if we change x a little bit, if we change y a little bit, then we are actually going to get a change in f that's approximately given by these guys.